again, we'll try and keep on time. So hopefully you've been able to see the box folder, the YouTube page, and Canvas. And with those three resources, you should be able to access all the information for the class. Again, mostly it's going to be PowerPoint slides, it's going to be some PDFs, and then it's going to be your own reading and literature papers and other stuff like that. So there is no book that you need. There's not a real good book yet for polymer additive, although there's some stuff in the library you can certainly look at. Of course, there's tons of things online. Some of the things online have more or less usefulness, but you can check those out. And if you see something cool online, you can shoot it up in the discussion section and say, hey, is this interesting or not? Do these people know what they're doing? Because sometimes the hobbyists really know what's going on versus it's just not yet in the literature. So anyway, again, the class is really, I will pick some of the topics and I will drive some of the discussion, but I think that being graduate students or advanced undergraduates or professionals, you get a lot more out of the class when you steer the conversation in the way you want it to be. So ask discussion questions, or in your homework number 1, say, I'm really interested in biomedical devices, or I'm really interested in cars, or how do you 3D print batteries? And I'll make sure to work some of those topics into the slides and into the discussion. And for your homework, I encourage you to pick papers that speak to you. And so some people have emailed me already and they say, what about this paper? What about that paper? Can I bring in some of my own insight, or should I cite some sources in my review? That's great. So if you find a paper that's kind of there, but maybe they didn't talk about some of the details, go ahead and bring in some of your own information. That's fine. It's really, the homework is there so I can give you a grade and you can actively participate in the class. And the homework is there to really challenge you to think about how to find information that's interesting to you in the literature, and how to dig a little bit for stuff that's either relevant to your research topic or relevant to your interest. So you can put on your CV, took specialized courses in additive with a focus on polymeric materials and composites for X or something like that. So, we will talk about some of the engineering parameters and the equations and heat flow and the characteristics of the process. But we have people in here from chemistry, from material science, from chemical engineering, from architecture, from mechanical engineering, from design. And so, it's not necessarily going to be a hardcore chemistry class or a hardcore math class. It's going to be a mixture of all these things together. So hopefully it'll give you more of an appreciation for the ecosystem of additive from a materials point of view. And so that's going to be a big part of it. And so if you're interested in specific materials, or if you're interested in some specific facet of additive and polymers, just let me know. I want to talk more about polymer chemistry, or I want to talk more about carbon fiber composites for use in windmills. I'm always open to stuff like that, and we'll cover a lot of that. All right, let's see. I look up because that's my screen in front of me, and otherwise I'm going to draw on my tablet here in a second so you can see my slides. Any questions or any points of discussion that are worth it for the whole class to hear? Of course, you can put things in the chat box. That's cool if I remember how to bring up the chat. Or stop me, or, we have just a few people online, so you can, just unmute yourself or something like that. Anything anybody want to chat about before we get going here? Okay. So hopefully people are getting a feel for what the class is going to be like and what my style is going to be like. But if things are getting off track and you're not comfortable, or you're not learning something that you really want to learn, shoot me an email. I'm happy to talk about whatever you want. I'm happy to arrange things so it's useful to you. I mean, especially in graduate school, you want to be learning stuff that is helpful to you. And so I want to be giving you that information and really helping guide you in terms of, you know, setting the stage, making the playing field for discussion, but then letting you all fill in the topics that are of interest to you. Okay, and again, I can't see the chat very easily on my tablet that I'm going to write on here, but I'll try and keep an eye on the chat on my computer in front of me. But you know, if you have a question or you need to stop or something, or you need me to stop or slow down, just let me know. Hold on, let me figure this out here. One sec. There we go. Okay, so we left off on a slide like this last time, and I'll go back one slide in a second, but this is again from this ASTM. Let me write that down. ASTM, additive processes. And ASTM really sets the standard for how we discuss engineering tests and physical science testing. You know, they publish a lot of mechanical testing standards, or a lot of the physical property standards. Like if you go to a lab like Westmoreland, or if you go to RJ Lee, you order materials testing by these ASTM tests, and they're certified and calibrated to do these ASTM tests. But ASTM does a lot of other types of things as well, including really defining what the playing field is for some of these physical science and engineering processes. So this is one diagram that they've published for additive, and this is really interesting to think about. So the type of intended product material is here at the top. And so if you're talking about metallic, ceramic, and composite, so composite is a generic term for just two different materials, but this is what they decided to do. You can start with the material, and then you have a thermal process. I don't know why they call it thermal reaction, but this is basically thermal bonding, so there's heat involved. Or you can have chemical reactions, and so of course you can have thermal plus chemical, like a thermally cured silicone or a thermally cured epoxy. And so there's some gray area here, but that's because there's just lots of chemistry available for polymers. But you have thermal processes and you have chemical processes. And then based on the type of feedstock you have, whether it's a sheet, whether it's particles, whether it's a powder, whether it's a filament, whether it's a liquid, you know, there's lots of different feedstocks and for additive. And this is what a lot of materials companies are interested in. So if you go by steel, or if you go by aluminum, or you go by polymer, generally you get a bar stock or a sheet stock, or in the case of polymers, you get pellets. But there's been a whole proliferation in the materials market for materials in the form factor that can be used in additive. And so what's the particle size distribution of the powder? What's the size of the filament? What do the pellets look like? You know, making composite sheet stock. Right now you can buy composite sheet stock for layup of carbon fiber sports equipment and things like that. But what other sheet stock is available? Are SLA resins, do they have the right viscosity? Can you buy the liquid precursors that work in stereolithography? So there's real opportunity here for invention in terms of the feedstock. So you just don't take something off the shelf like you do for a regular thermoforming process. So if you're familiar with thermoforming, and we'll look at some of that later on, you buy a big sheet of thermoplastic material, you put it in a vacuum thermoformer, you heat it up, and you turn it into a Halloween mask or something like that. That type of feedstock is not necessarily appropriate for additive. And so, you know, if you work for a materials company like Arkema, that's a big polymer company in Pennsylvania. Even though they're French, they have global office here in King of Prussia, right by the mall. Or if you work for Dow or DuPont or some other big materials company or Arconic, they're really interested in what do they have to do to their products in order to make them additive products. And they don't necessarily invent brand new materials, but they try and get the materials and the knowledge and the chemistry that they have into an additive format. So there's a lot of opportunity there. This next box is really interesting because it starts to set up the connection between the materials and the process. And we talked about that last time. So here you have materials. And here you have process. And embedded in the process is energy and geometry. So what type of energy source are you going to use? And what is the geometry that you're going to use in order to contain the raw material? And so when you read papers about additive, of course, you're looking for the material because that's what people are going to work on. But you want to think about what process are they using? What wavelength light are they using? What temperatures are they using? Are they using IR heat? Are they doing something else? What laser power are they using? Those are all really important things. And then the geometry is how you bring the feedstock and the energy source together. Is it top-down stereolithography? Is it bottom-up DLP stereolithography? Are they doing powder bed fusion? Are they doing something else? And so there are all kinds of different tweaks and all kinds of different small variations in processes and materials that you have to pay attention to really understand this whole world of additive and materials. And some of you will work for 3D printing companies or companies like General Motors that want to use additive manufacturing. And so you have to understand all the little tweaks so you can invent and excel in this area. So this, a type of diagram like this sets the stage for how to think about these processes. Then we have the basic AM principle, which is interesting. So are you fusing sheets? Are you solvent reactive curing? Are you light reactive curing? We'll talk about all these things. And of course, the AM principle needs to be matched to the characteristic of the polymer. So you're not gonna light reactive cure a thermoplastic because that's not how thermoplastics are processed. Or you can't do powder bed fusion of a liquid resin because it's not a powder. Or just because you can make a polymer powder doesn't necessarily mean you can do powder bed fusion, because the physics of powder bed fusion, your polymer needs to have certain characteristics to be amenable to that process. So this sort of helps you decide what's possible and how you match up materials and processes. Okay, so we have the principle, we have the process category, and then this one is really interesting. And this term, I don't know if people know about it other than if they've studied ceramics or these sintering processes, but green bodies. So green body in traditional ceramics describes a part that's shaped but doesn't yet have the final properties because it hasn't been sintered or it hasn't been compacted. And so we can also say we could have a green body that's a metal. So a powder bed fusion part might be fused, but it doesn't have its final properties yet because it hasn't been high temperature isostatically pressed, or it hasn't been hipped, or it hasn't been finished, or something like that. So this idea of a green body, and I'll just write that down, usually mean a part that's been shaped, but it hasn't been post-processed. And everyone knows that the secret to additive manufacturing is you need good post-processing. And so we'll talk a little bit about post-processing in this class, but post-processing is sort of the traditional part of additive after all the additive action is over. And so you have your SLA process, there's lasers, you know, it's cool, you have shapes appearing out of your vat. That's really awesome and interesting, and that's what a lot of us are here to learn about. But that part that just came out of an SLA process, say from carbon or someone like that, needs to be solvent washed, needs to be thermally cured. Maybe you need to machine it a little bit to get the right dimensions. And so oftentimes you see these really cool additive demonstrations or these additive videos, but they forget to tell you about all the post-processing that goes on after you do the additive. And we'll watch a couple of those videos because it's in there, but they just sort of gloss over it. Or if anyone's ordered a part from Shapeways, or if anyone's ever done a powder bed fusion part, you know that there's a lot of post-processing to come from that. So make sure as you're learning about additive that you get an idea of course, the connection between materials and process, but then post-processing is how we get actual products to use rather than just some shape to look at. Okay, let me check the chat here. Any questions so far on this? All right, keep going. Feel free to just pop things in the chat or unmute yourself, that's fine. So this is just putting a finer point for polymers on it. So this is the slide we ended up on last time. And so hopefully through the box, the notes are annotating. So after we have a lecture, if you go back into box, wait a couple minutes for everything to update, you'll be able to see my notes on there. And of course, you can download the blank slides as well. So if anyone gets lost in terms of what's happening on box, just let me know. But anyway, for polymers and let's say polymer-based composites, this is the ASTM landscape that we're interested in. So we won't belabor this, but it's worthwhile to have your eyes on the ASTM nomenclature. So it's not called stereolithography, it's called vat photopolymerization, or it's not called fused filament fabrication or FDM, it's called material extrusion. So make sure that you're using some of this standard nomenclature so we're all on the same page, because different companies will call their processes brand names or different things. That's just more of a branding or industrial exercise. We want to talk about the scientific and engineering basis for what's going on and try and leave the hype to people who get paid to hype things. Okay. So we're going to talk about polymers. And, you know, it's really hard to draw polymers because they're very long and very skinny, or they have a high aspect ratio, but we're going to draw polymers that look like this. And so there's a couple interesting characteristics about drawings like this. And I just want to set the stage because we're going to talk about molecules. We're going to talk about long chains, and the way we represent those long chains is with these stick figures. So the polymer on the right here is called a semicrystalline polymer. And of course, semi means partially or a fraction of crystallinity. And so this part is a polymer crystal. And we represent it as a chain folded lamellae. So that's the standard understanding of polymer crystallization. So if you're confused already, you'll just have to do some polymer studying, and I can send you some resources online. But if you've taken a polymer science course, you should be all set. So semi again means partially. Does anyone know what the other phase is in a semicrystalline polymer? So of course there's a crystalline phase or chain folded lamellae phase, but what's the other part of the semicrystalline material? You can type it in the chat or just pipe up. It's not crystalline, it's what?
Amorphous?
Amorphous, perfect. And so the amorphous part of a semicrystalline polymer is in between the crystals. And so the one big difference between polymers and all the other materials is that there's no such thing as a 100% crystalline polymer. So even single crystal polymers have enough defects and have chain folds that there's still an amorphous of small amorphous fraction in single crystals of polymers. So we will always call them semicrystalline, and that implies that there's both amorphous and crystalline parts in this semicrystalline polymer. And that's an important distinction because the behavior of a polymer crystal is different than the behavior of an amorphous part of a polymer. And we'll take advantage of that in additive processing. So that's a really important concept that you should know and understand. And if you don't get what I'm saying, we can talk about it in office hours, or I can send out some resources. So if it's not a chain folded lamellae, and a chain folded lamella or lamellae is going to look always like this. So that's how I'm going to draw a polymer crystal. This is just a big glob of amorphous polymer. Now, it's hard to tell if this amorphous polymer is cross-linked or not. We'll generally draw cross-linked polymers like this. And so this thing is cross-linked plus amorphous. Now, there are such things as cross-linked semicrystalline polymers, but they're not super common. And so generally you'll have fully amorphous polymers, you'll have cross-linked polymers that are generally amorphous, and then you'll have semicrystalline polymers that are generally all thermoplastic. Oh, I see a question here, one sec. The opposite can be true though, right? Some polymers can be 100% amorphous. Yes, yeah, of course. So there are some polymers that don't crystallize at all and never will. And so that's also really interesting because of course some metals you can have amorphous metals or bulk metallic glasses, which are like amorphous metals. But if you process those a different way, of course you can get metals to crystallize. Some polymers like polystyrene will never ever crystallize no matter what you do, no matter how long you wait. But because of the wonders of organic chemistry, if you make syndiotactic polystyrene or if you make regioregular polystyrene, it is semicrystalline. And so that gets in the weeds of polymer science and how you design different polymers. And so feel free to keep asking those questions. I'm not going to give you a lecture on stereochemistry in this class. I'm sure some of you don't want it. But if you have some of those deep polymer science questions, you can take a polymer science class, or if you've taken polymer science or composite science class and you're like, hey, I learned this term, is it important in additive? We can certainly talk about that. Okay, so that sort of sets the field. And last time we talked about the thermal transitions of polymers, and the two that we care about a lot are TG, TM, and then there's also something called TD, which is the decomposition temperature. That's not really a thermal transition other than to say it's a temperature that we want to avoid. And if we're trying to look at a processing window for a polymer, of course, we need to be lower than the TD. But TG and TM are the important thermal transitions that we'll talk about to begin with. So TG refers to the glass transition temperature, and that's an amorphous phase transition because liquids are amorphous, glasses are amorphous, and TG defines the temperature where a material transitions between a liquid and a glass. And a TM, a formal melting temperature, which is a first order phase transition, only exists for crystals. So there is no such thing as a TM of an amorphous polymer. Amorphous phases always have TGs, but a polymer crystal will have a TM. And the amorphous part of the polymer crystal will have a TG. So in a semicrystalline material, there's at least two thermal phase transitions the Tg of the amorphous part and the Tm of the semicrystalline part. And this might seem like it's esoteric now, just looking at these diagrams, but this comes into play when we talk about processing these materials and what happens when we cross these thermal phase transitions in our process. So again, this sets the polymer science stage, and we'll overlay the additive manufacturing ideas on top of this. Okay, so how do we find these thermal transitions? We use something called DSC, or differential scanning calorimetry. So this is called DSC. So it's called differential scanning calorimetry because it's measuring this thing called heat flow. Heat flow, and it's measuring the heat flow as a function of temperature. And if you measure heat flows, that means you can measure enthalpies, especially if you're measuring against a reference. That's where the differential comes from. And so you don't need to worry about the details of the measurement, but this diagram now gives us an idea of the processing window and the thermal transitions for a given material. So when you read an additive paper on thermoplastics, so you can do DSC of thermosets, but let's focus on thermoplastics. All good additive papers will run the DSC to show you where the thermal transitions are in their feedstock and then design the additive process around it. So you see labeled in this diagram is the TG, which is this baseline offset, and that's a second order phase transition. We can talk about that if you want, but this change in heat capacity is what defines a second order phase transition. And this peak is a crystallization peak, so we can call this TC, and that's related to what we just talked about, a TM, which is a first order phase transition. So there's an enthalpy of melting for that. So this diagram is really interesting because if you think about molecules that you know a lot about, like water, what is the TC of water? Someone can pipe up or they can put it in the chat. So water has a TC of what temperature?
0 Celsius?
0 degrees Celsius, that's right. What's the TM of water or ice?
0 Celsius?
Yeah,
0 Celsius. That's right. It's not a trick question. So water will have a TC and a TM at the same temperature, 0 degrees Celsius. And it turns out there's a TG of water. It's like minus 170 C or something. We won't worry about that. But a lot of small molecules have TGs as well. But in small molecules, we all know that the melting temperature and the crystallization temperature are usually the same temperature, right? But in polymers, that is not true. The TM and the TC are different because of the unique macromolecular nature and the unique chain-folded lamellae crystal character of that. So that's really interesting. Thermodynamically, at infinite cooling limit, TC and TM are the same, but we won't talk about that in this class. That's sort of in the weeds polymer science. But what you need to know for this class is when you melt a polymer and then you cool it down, it is going to crystallize at a lower temperature usually than what you melted at. But there's all sorts of other things that can happen, like you can have crystallization on heating. So as you go above the glass transition temperature, all of a sudden you have some crystals form. And so this is how we do annealing of polymers. So we anneal above TG. And there's lots of cool stuff that you can do. Like you can strengthen materials by annealing them above TG, just like you can increase the grain size, or you can change the grain size in metals or ceramics or something else. So there's a lot of things wrapped up in here, but looking for these differential scanning calorimetry data and connecting it to your additive process tells you a lot about what's going on, assuming that you're processing a thermoplastic. And we'll look at DSCs of thermosets as well, because that tells you other things that you need to know, like curing temperatures rather than thermal transitions. So again, being able to identify these different thermal transitions and measure them is important. And you'll see things in technical data sheets like the heat deflection temperature or the melt flow index or some of these other engineering parameters for polymers. Those are useful for other things, and we'll talk about those in class, but really we want to go to the heart of the polymer science and how to think about polymers and additive, and that starts with TG, TM, semicrystalline, and amorphous polymers. Any questions so far? All right, I don't see anything in the chat box. So this gets back to the point that I mentioned on the previous slide, that TC and TM are different in polymers, and we can also vary the TM by changing the lamellar size or the crystallite size. So as we change this LC right here, so that's the lamellar thickness or the thickness of the crystal, you see that the TM changes. So this is thicker crystals, because this is 1 over LC, this is thinner. So this makes sense. Smaller stuff melts at a lower temperature, and larger stuff melts at a higher temperature. And eventually, if you extrapolate this to 0, so 0 on this plot equals 1 over infinity. This is an LC equals infinity. And that's the thermodynamic melting temperature of the polymer, or what we call TM0 at LC equals infinity. So if you want to study the limits of this, you can look up the TM0 of lots of different polymers. But usually the TM will depend on the crystallite size. And the crystallite size, we can vary LC by changing processing or crystallization temp. So we actually get, in a lot of processes, in a lot of polymer processes, we get to control the crystallization temperature. We're going to melt this polymer, so it's all amorphous. So remember, this is also a picture of a polymer melt. When we're above TM, we don't have any crystals. And then when we go below TM, down to a TC, we get some crystals forming. But we get to pick that crystallization temperature. And so we can dial in our crystallization temperature to dial in the crystal thickness, and that dials in the melting temperature. And so those things are connected in polymers, and that's something that we can control. It's how they do injection molding. This is going to be the crystallization temperature because we want this type of crystallite size to get these properties. But that's something to think about as we're putting polymers or thermoplastics through an additive process, what happens to the crystallite size, etc. And this will become important for material extrusion, AM, and also for powder bed fusion, because we can start to control these temperatures.
Oh, Mike, I have a question.
Go for it.
I was going to ask, does molecular weight have an influence on crystal size?
So to a first order, no.
Okay.
However, it can influence the rate of crystallization, and the rate of crystallization can influence the crystallite size. Of course, lower molecule things or lower molecular weight things will crystallize faster. And so that could change depending on your process. Like sometimes for processing a part, we're not holding it at one temperature. Maybe we have a drift in temperature, or maybe the part is cooling down more slowly. So molecular weight can have an influence, but we don't have any plots like this of TM versus molecular weight. It's always some other type of characteristic of the crystal, usually crystallite size. So it's not a direct relationship, but of course it's a polymer, so molecular weight's always involved somehow.
Thank you.
Good
Can I ask
question.
how much pressure influences crystallite size and TM?
Yeah, so polymers are incompressible fluids because they're liquids, but there are some studies of very high pressure, and they do influence the thermodynamics of polymers a little bit. But pressure is not a major variable. And certainly the pressures that we process polymers at, even if it's 200 psi, 300 psi, 500 psi, those aren't high pressures compared to an incompressible fluid like a polymer. But people have done some scientific studies at like a gigapascal or 20,000 psi, you know, these high pressure thermodynamic studies. And there are some variations in polymer properties way up at those high pressures, but pressure is not a main variable in these types of thermodynamic characteristics, because polymers are like liquids. So just like water, the crystallization temperature of water is 0 degrees Celsius over a large range of pressure. You have to go to crazy different pressures to start to get a variation in the thermodynamic properties of water. Same with polymers, and that's because it's an incompressible fluid. Does that make sense? Yeah. Now,
Yes, sir. Thank you.
now pressure has a huge influence on flow rate and viscosity and other things, and so we'll talk about that when we get there, but not for these thermodynamic considerations. Good questions. Anything else before we move on? All right, as Locke alluded to, molecular weight is really important. And it turns out that the glass transition temperature, not the melting temperature in this case, but TG really depends on molecular weight, because this curve defines when is a polymer a polymer. Of course, if the molecular weight is too low, down here, this is called a monomer. And I'll remind you, just like we talked about last lecture, you know, if we're interested in ethylene or polyethylene, we start with a monomer that has a molecular weight of 28 grams per mole, and we can make polyethylene that's 1,000, 100,000, million, 10 million grams per mole. And that's really illustrated by this diagram right here. So we have monomer, and then we have polymer. And the definition of a polymer is this plateau molecular weight. And so a polymer is a polymer after it crosses the plateau molecular weight, because there's not a big variation in TG as a function of molecular weight anymore. What do we call things that are between monomers and polymers?
Is it an oligomer?
Yep, that's right. And we're actually going to talk a lot about oligomers. Oligomers are a very important part of processing polymers, because sometimes we need a low glass transition temperature, or sometimes oligomers are very good viscosity modifiers before we get to a polymer. So especially in things like Brianna's been interested in, like SLA, you start with oligomers and then you make polymers from that to solidify the shape. But if you make an oligomer of polystyrene, so this is 100 grams per mole right here, if you make 100 grams per mole polystyrene, it's not going to be that awesome because it's going to have a low glass transition temperature. You really need to be 1,000, 20,000, 30,000, and higher in order to get polymer behavior. Now, why don't we just make polymers all 1,000,000 molecular weight? Why don't we just say, I'm just going to make every polymer way out here. I'm going to make everything 10 to the 6th. Why don't we do that? Just go way above the plateau molecular weight and call it good. Can anyone think of a reason why we don't want to do that, or what might some problems be? So
How about a high viscosity?
yeah, that's exactly what I was gonna say. So higher molecular weight equals higher viscosity. And higher viscosity is going to take more energy to process, as you'll see. Sometimes it's expensive to make those high molecular weight polymers because you have to wait for a long time for the reaction to be completed, or you have to take out all the monomer to drive the reaction to high molecular weight. But this issue of higher viscosity is a real problem, especially if you're already on the plateau molecular weight. So if you're interested in the heat deflection temperature or having a thermally robust polymer, all you need to do is get up into the plateau molecular weight and then you're good. You get that heat resistant property. But if you keep going higher and higher in molecular weight, the polymer is getting more and more viscous, but the TG is not going up. So you're not gaining any benefit because you're going to have to process this super high viscosity polymer, and you're not going to get any property benefit in the final product. And so when people make things like Spectra fibers, which are ultra high molecular weight polyethylene, or you're making hip sockets or medical implants from ultra high molecular weight polyethylene, they're doing that for a reason, to get the properties they want. But most polymers that you buy on the open market for injection molding or extrusion or blow molding or something like that all have a molecular weight that's tuned to get the properties that people want in their final products, but not have to deal with these really high viscosities. And we'll talk about the influence of viscosity in a bunch of different additive processes. But that's why polymers are not made at really high molecular weight all the time, because in order to process them, you need to dial in that viscosity. And a lot of times the viscosity or the molecular weight is tuned to get a specific viscosity. So that's what Dow Chemical Corporation and ExxonMobil and other people who make thermoplastics worry about. How do I get the right molecular weight so people can process it and still get the properties? So that's interesting. So when you read your papers or when you do research on additive, of course, if it's a mechanical engineering group, or if it's a design group or a civil engineering group, they're not always going to say this was a molecular weight. Or if someone's just buying a reel of Ninja Flex, let's say, or a reel of polypropylene from Verbatim, they might not know the molecular weight. And so you sometimes need some inside information, or you need to do some digging to figure out what the molecular weight is. But there's some proxies for molecular weight that we'll talk about, because not every polymer has its molecular weight measured or reported. There's some other things that we measure that gives us an idea of what the molecular weight is. Any questions on molecular weight and why it's important for polymers?
Hey, Mike, I got a question.
Yep.
Can you use DSC to find out the molecular weight based on the TG?
No, because for most polymers, you're going to be at the plateau molecular weight. And so the DSC will give you an idea of the molecular weight, just so you're above the plateau. I guess if you're in here, maybe, but that's not really, DSC is not a very direct measurement of molecular weight, because you usually don't have a calibration curve like this. So not every polymer has quantitative TG versus molecular weight characterization. But there is a lot of viscosity versus molecular weight. There's a direct way to measure molecular weight, which is called size exclusion chromatography. And so there are ways to directly measure molecular weight, just not DSC.
Okay, thank you.
Great. All right, so this is just one plot to add to this viscosity discussion that Ben brought up, is that we just looked at this plot, property X, and this solid line is property X versus molecular weight. And so again, this is the plateau. So whether you're interested in modulus or whether you're interested in TG, they all have plateau molecular weights, and they're usually close to the same value. But viscosity has a different relationship. There is no such thing as a plateau molecular weight for viscosity. This is the viscosity line. So viscosity is the dashed line. So below the plateau molecular weight, you have scaling of molecular weight to the first power for viscosity. So that's what MW raised to the 1.0 means, which is a linear relationship between molecular weight and viscosity. So if you're below the plateau molecular weight, and let me define that the plateau molecular weight is this number right here. So there's only one plateau molecular weight, and that's it. So below the plateau molecular weight, if you double the size of the oligomer or you double the molecular weight of the oligomer, your viscosity is going to go up by a factor of 2. That's fine. You know, you make the molecule twice as big, the viscosity is twice as high. You make the molecule 4 times as big, the viscosity is 4 times as big. We can sort of get that. Above the plateau molecular weight, however, you have this relationship. And this relationship is molecular weight to the 3.4 power. So this is called a scaling relationship. Sometimes you might call it a power law. But now this is an exponential relationship between molecular weight and viscosity, and it's molecular weight to the 3.4. So if you double the molecular weight, it's 2 to the 3.4, which is, does anyone know what 2 to the 3.4 is? Let me get out my calculator. Let's see. 2 to the 3.4 is 10.55 or 10.56. And so if you double the molecular weight, the viscosity is going to go up by a factor of 10. And so that's really interesting, is this scaling relationship. If you move on this curve too much, the viscosity shoots up. And you can take Professor Colby's polymer physics course to figure out why it scales to the 3.4 power. Professor Colby was in polymer science when that relationship was invented, and so that's called the field of polymer physics. But it's really because of entanglements. So this plateau molecular weight defines the onset of entanglements. So there's something called an entanglement molecular weight. I don't know why that's fat there. There's something called an entanglement molecular weight, but this plateau molecular weight occurs because you have entanglements. And entanglements are basically one polymer entangles with the other. So you can think about this in terms of, let's say, spaghetti. When the spaghetti is uncooked, it's all rods. And so you can just pick one up and you can just take one out and it doesn't stick to anything else. But cooked spaghetti, if you try and grab one noodle out of cooked spaghetti, you're usually going to get a lot of other noodles coming with it. And so cooked spaghetti is entangled, and, excuse me, and uncooked spaghetti is not. And so that's the difference, that these entanglements drag a lot of other molecules with them. And that's why you see this shooting up in viscosity. So again, there's a lot of polymer science behind this. If you're interested in understanding more about this, there's plenty of polymer courses you can take from the polymer science faculty at Penn State. We've got lots of awesome people that talk about this. But this is now some of the physics that we're going to have to think about as we start to design our additive process. Any questions? All right, and we're going to start to talk about additive processes in the next set of slides, and we're going to talk about additive molecules here in just 1 second. So bear with me. We're just setting the stage for what polymers are before we talk about polymer and composite additive.
Sorry
So-
for the delay. Sorry for the delay. I do
Go
have
ahead.
a question. Just
Go
had
ahead.
one come up. If you can go back to the last slide. Is there any significance where the viscosity line, the dashed line, intersects the solid red line, the polymer line? Is there any significance there?
Nope, nope. These axes, the viscosity axis and the property x-axis, are just schematics. So there's no scaling between those. So there's no significance of that crossing point. That's just a quirk of the graph.
Okay, thanks.
Good thought though. I mean, that's what you want to look for in plots, right? What are the inflection points? What are the crossing points? Where does it hit the origin? All of that stuff. So that's good graph reading tendencies right there. Sometimes the two y-axes are coupled, and so it's good to know when you have a coupled y-axis. So sometimes we call this the primary y-axis and the secondary y-axis. So it's good to know when they are coupled by physics versus when they aren't. And in this case, there is no coupling between the two y-axes. They're totally independent. So I've shown you using DSC how polymer scientists measure thermal transitions. And so again, this is a differential scanning calorimegram. And so you can see a lot of these in the literature, and you can look up these for lots of different polymers. So if you're like, I wonder what the DSC looks like for polypropylene, or I wonder what the DSC looks like for PET, you can find that in the literature. Polymer scientists measure viscosities like this. And so this is not viscosity on the y-axis, this is modulus. And this is E prime is called, or G prime is called the storage modulus. There's something called E double prime or G double prime. That's called the loss modulus. We'll talk about that in a second. But we measure the modulus because it gives you an idea of the physical properties of the polymer across a very large temperature range. So glasses have moduli. Of course, semicrystalline polymers do. Rubbers have moduli, and liquids have moduli as well. And so this type of plot, and this is called rheometry. And we measure it. The instrument's called rheometer. And this field is called rheology. Whoops. So you have the science, you have the instrument, and then you have the measurement system. And so this is all in the world of rheology. So you can go to a rheometer and you can measure the modulus of a polymer over the glassy region, over this called the transition region. So when we go from glass to rubber, what thermal transition is that? What's the thermal transition between a glassy material and a rubbery material? What's that called? It's an easy one. The glass is transitioning, right? TG. All polymers have a TG. Every single polymer has a TG with no exceptions. Sometimes they're hard to measure, but everything has a TG because all polymers have some amorphous part. And so when you transition from a glass to a rubber, you have TG. And you notice that this TG is not a sharp temperature. It's usually a range over 5 or 10 degrees Celsius. That's this little kink on the DSC. So you notice that this DSC has a little temperature range there for the TG. Oftentimes we quote one value, which is the inflection point or the halfway point, but the TG is a second order phase transition. It occurs over a temperature range. And so that's why we have a transition region defined here. But you notice that a glass is high modulus or hard. So when we say a glassy polymer, it's glassy. It's like glass, like window glass. You know, it's hard. Rubbery polymer has a lower modulus. And so rubbers are really interesting materials because you can have a really soft rubber like a rubber band, or you can have a really hard rubber like a car tire, or you can even have harder rubbers than that. And so there is no one modulus that we really say, this is how a rubber is defined. Rubbery materials are defined over a range of moduli. And we'll get familiar with a bunch of different rubbery materials that are useful in additive. And then if you take a rubber and you keep heating it up and it's not a cross-link rubber, eventually, if you heat up a material high enough, what do all materials turn into before they turn into gases and break down? What's the last phase here? A liquid or a melt. And of course, liquids and melts have very low moduli. They flow. But you notice that depending on the molecular weight, the TG is about the same. The glassy region is about the same, but they will start to liquefy, or they will start to go into a melt. This is not a TM. This is called a polymer melt, which is basically just a polymer liquid, which is basically just a really warm rubber that starts to flow. And so liquids or melts are flowing polymers. And this shows that it's not cross-linked. Well, let me just put cross-linked. We'll see some examples where this rubbery line keeps going and going and going, and this is a cross-linked rubber. And so in order to process a material, if we're going to process a thermoplastic, we can't process a glassy thermoplastic in a 3D printer because it has too high a modulus. We can't get anything to stick together. And we can't be too close to the TG because the TG is a range, and above the TG, we just have rubbery materials. And it's really hard to get rubbery materials to stick together. We really need to be in this melt region where we process thermoplastics here. Sorry, that's getting crowded, but hopefully you're taking some notes at home. But you really want to process thermoplastics in the melt region. And so it's really helpful to know what the rheology is of your polymer to define the thermal transitions, and then you can relate this to viscosity. So it turns out that a modulus of a liquid or a modulus of anything, this E prime, can be related to a viscosity, and we'll talk about that. but you really need to have very low modulus in order to have a low enough viscosity polymer that you can get it to stick together. So not only do you need to shove a thermoplastic through the orifice of a MakerBot, but the viscosity of that polymer needs to be low enough that it will fuse to the next layer. It's really hard to fuse two super balls together, right? They're cross-linked, they don't want to fuse, you can try and jam them together, nothing happens. But if you wait long enough, you can fuse two balls of silly putty together. And so you can slowly squish them together. Of course, they bounce off one another if the time scale is too short. We'll talk about the time scale part of this in a second. But you really need to have low viscosity to get good fusion. And to do that with thermoplastics, you need higher temperature. So we're going to have a whole lecture or a couple lectures on what we call road adhesion or road fusion, and it all depends on the temperature and the rheology of the polymer. So just like DSC, you can find these plots in polymer science textbooks. So if you go and look up the modulus versus temperature data or the rheology data for 50,000 molecular weight polyethylene, or if you look this up for PLA, you can often find these types of measurements in the polymer science literature, or you can go to Professor Colby's lab and measure these things in the rheometer, which will give you, along with the thermal transitions, will give you an idea of how to process whatever polymer you're interested in additive. So that's how we take some of the polymer science of thermal transitions, molecular weight, and rheology, and put them together to do polymer processing. And this is exactly what they did when they invented extrusion and other types of conventional polymer processing. And we're basically doing exactly the same thing now, only with a new world of additive manufacturing. Any questions? Any discussion points, things people want to talk about while we have a pause here? All right, we have about 13 more minutes, so we'll keep going. And I promise you we're going to get to additive in a second here after we cover just one or two more things. So this is really just of interest because, of course, as we change the molecular weight in small molecules now, this changes the melting point. So these are for waxes, not polymers. So sometimes you see things like this, and that's due to the interesting things that happen when you crystallize these short alkanes. But I just wanted to put that in there so you saw that. Now, this slide is really important because this is one of the things that is going to confuse you as you start to read papers. So you're going to see terms like HDPE, or you're going to see terms like high density polyethylene, or you might see something like a brand name like I don't know what a good brand name is for HDPE, but you might see something like Dowex, even though Dowex is not polyethylene, but you'll see a brand name. So you'll see a brand name. You'll have a technical abbreviation. You'll have a technical name. And then, of course, you can combine this with a chemical structure for polyethylene. And so you'll have all of these things connected. And depending on who's talking about the polymer in whatever book or whatever paper, they might say we're using HDPE or we're using Dowex or whatever brand name is for that polymer. And different companies have different brand names for exactly the same polymer. So ExxonMobil has a different brand name for their polyethylene versus Dow. And so you want to make sure that you're able to connect the polymer to the company to actually what it is. So in polymer science and engineering, we care about this, but brand names sometimes are how you buy polymers. Brand names will be reported in the literature. And so you really want to keep your wits about you in terms of, oh, they're using NinjaFlex. What polymer is NinjaFlex? How does it work? Or, oh, they're using Kraton G. What is Kraton G? What's the chemical structure? What are the thermal transitions? And so this is where the literature can get really confusing if you don't have someone to guide you through this nomenclature, or if you don't ask questions. And so in your first paper that's due a week from today, and it's due by midnight, just because that's how I set it up on Canvas, so I don't have to click some extra buttons and set a time. So just get it in on that day, no matter when that day is, and that's fine. Of course, you can submit things early on Canvas too. If you have problems with the Canvas submission, if Canvas is new to you, just let me know. But don't email me the paper because I might lose it. Please submit it on Canvas so I have a record of it in class. But this is where, when you do your first paper, I'd really like to see some people say, oh, they're using this polymer and they said it's PLA. These are the characteristics. You know, it's polylactide or polylactic acid. It's from this company. But sometimes that's hard to track down. Like if you go to Matter Hackers, which is a place that supplies filament for 3D printing, they don't tell you where the polymer comes from. Sometimes they give you the brand name and the technical abbreviation, but they don't necessarily tell you what company it's from. Or if you go buy a Formlabs SLA resin, they'll say, oh, this is Formlabs Flexible, or Formlabs Tough, or Formlabs Prototyping. They don't tell you the chemistry at all. And so this is something that you need to keep in mind as you think about what feedstocks are out there for additive and what it really means when you get a bottle or a bag of something from a company. Some companies really don't want to tell you what's in there because that's their secret information, or they don't even think about it or don't know necessarily themselves. They're just sourcing it from somewhere. So this is just one slide to remind you to be able to connect all of these different facets of what plastics are, because this allows us to make some sense out of them in terms of materials. Any questions on this? And certainly if you run across a polymer in a paper that you don't know anything about, put it up on the chat. Certainly someone will know something about it, or I'll know about it. But if it's an open question that the class would benefit from, go ahead and put it up in the the discussion group on Canvas, because people will be interested in seeing that. Any questions? All right, couple more minutes. This just defines what TM and TG are in terms of first order or second order phase transitions. I'm not going to belabor this, but if you're interested in the thermodynamics, that's fine. What's interesting in this plot is V here stands for volume. Or in scientific words, we might call this specific volume. So this is interesting now because you know this plot shows you when you cross the TM, you have a delta V. So a melt, of course, is hotter, so it has a higher specific volume, and a crystalline solid is lower in specific volume. And so when you crystallize a polymer, it might go from 1 cubic centimeter to, let's say, 0.97 cubic centimeter. So it contracts, or the specific volume gets smaller. That also occurs in the rubbery to glass transition temperature. So the slope of this line is the CTE, but there's a discontinuity in the CTE between a rubber and a glass. And so that's really interesting because when you cross a thermal transition, you get a volume change. So this is a scientific plot from Polymer Science. Why do we care about this for additive? Why do we care that polymers change volume when we cross the thermal transition? Why is that important? Has anyone ever printed something on a MakerBot? You know, if you haven't seen an additive process happen in real life, go ahead and go on YouTube. I'll give you permission to do some YouTube homework and just watch some additive processes online. I'll show some videos as well, but I'll show some videos that for very specific reasons. But, you know, just check out some of the printing videos. And I'll go back to my question. Why is a volume change important, or why do we care about a volume change in additive manufacturing of polymers and composites? Go for it, Eric. Is that a hand? Go ahead.
Yeah, it is. If you have a volume change as your material is cooling, it's going to lead to warpage and cracking and all kind of internal stresses.
That's right. Internal stresses is a real big one. So warping, internal stresses.
And I guess if it gets worse enough, then you get cracking. Bad enough.
That's right. You can have internal stresses or internal stress. So you have internal stress first. If it's just a little bad, you get warping. If it's really bad, you get cracking. And it turns out that this is one of the really big issues in additive for all kinds of materials, because all materials have a CTE. And a lot of additive processes are going to have temperature variations. And so this happens in metals, this happens in ceramics, and this happens a lot in polymers. And we'll talk about this warpage. And I think lots of people have a sense for what warpage is, but this is a scientific reason why it happens. And so when you talk to people who design additive processes, they're really concerned about what is the CTE mismatch, or what is the warpage of this material, or how do I dewarp a material, or how do I post-process to relieve stress or warpage. If you processed metals, there's always some stress relief after you do cold rolling or hot isostatic pressing or something like that. But you can also stress relieve polymers. You can also anneal polymers to get rid of warpage. And so that's something that we'll talk about, because that's a really important part of additive, because additive, you're shaping the part that you want as you're processing materials. Now, we had to deal with this in injection molding and all types of other polymer processing, but it's been handled in those other technologies because they've been around for a long time. Additive is relatively new in the world of polymer processing, and so we're still trying to figure out techniques for dealing with stress relief, for dealing with warpage, for dealing with post-processing to get rid of these issues in polymers. So again, this is the scientific reason why, and you'll see this happen as we start to look at different additive processes. So that's good.
I have a question for the last.
Go ahead, Jivtesh, go ahead.
Is there a way we can change either processing or the actual polymer to reduce the CTE difference between glass and rubbery?
Yes, yes. So you need to consider polymer, process, and process time, and process temperature, or conditions to combat this. So You'll see in some additive processes that we talk about in material extrusion, those processes will be done in an oven. So some 3D printers have built-in ovens to get rid of warpage, because if you're transitioning a big temperature region, of course, you have a big delta V for large temperature swings. But if you can really control the temperature, if you can keep it in a small range, you can still get your glass to rubbery transition, which is what you need, but perhaps you're not traversing as high of a temperature, or you're keeping the part more isothermal. And of course, the more isothermal something is, or the more something stays at the same temperature, the less internal stress you're going to have, because if the temperature is constant, the volume is going to be constant. So this is really where there's no magic bullet or one solution. This is where the process now is coupled to what your goals are. And, you know, let's face it, sometimes it's easy to put a 3D printer in an oven. Sometimes it's hard. That oven costs money. And so sometimes we'd all like to buy a nice heated material extrusion AM printer, but that's not always possible. And so we need to think about, you know, what's the expense of the machine? How easy is it to use? And a lot of these other factors when we start to think about what's possible in our process versus just buying a MakerBot or something else that's at ambient temperature. That's a great question to end on. Is there any final stuff here? We're at 2:50, so I'm going to try and stop on time. Is there any final stuff people want to talk about? Okay, so we'll pick this up on Tuesday at the same time, and I'll post this YouTube video when I have it. But again, it's this connection between materials, process, and now conditions, or the different physics that happen to the material and the process conditions. And we'll start to build up the story first for FFF, or material extrusion AM, so MakerBot style printing, if you will. But then we'll go on to SLA, powder bed fusion, all the different processes in the ASTM diagram that have to deal with polymers and composites. And eventually we're going to talk about how this picture changes for composites. What does TG and TM mean for composite materials? And so we're slowly building our way up the picture of how polymer science and additive manufacturing intersect along with composites. So thank you very much. Please shoot me those emails if you have questions, or put something up on the discussion group on Canvas. And I'm available anytime to Zoom if you want to chat. So thanks a lot. Hope everyone is safe and healthy out there, and I will see you on Tuesday, same time. Thank you. Bye-bye.
Thank you.
See ya.
Thank you.
I have a question. Are you available to talk right now?